Hello all, this is a review report presentation on edge-based hybrid system implementation for long-range safety and healthcare IoT applications. This paper was published in IEEE IoT Journal, Volume 8 and number 12th paper on June 15th, 2021. This presentation will be carried out by me and my two teammates, Krishna and Sahil. This paper offers a solution to the following issues. Typically, the most significant difficulty encountered by any short-range IoT applications are as follow. The number of gateways in the network is considerable, making it particularly pricey for short-range IoT nodes. If cloud computing is employed, then the system will be affected by any service interruptions, since the IP connection will be discontinuous. This is due to the fact that all data handling is performed in the cloud. In this research, we present an edge-based hybrid network system architecture in an IoT scenario that is both cost and energy efficient. This design is intended for any short-range wireless IoT protocol applications that demand real-time and low-latency feedback. This is accomplished by linking low-power wide area networks, that is LPW, and low-power WANs to end nodes, thereby expanding the range of wireless networks, and further through edge gateways, which provide low-cost local edge services for a variety of IoT devices. In doing so, the need for multiple gateways is reduced. The design and implementation of the edge layer in the IoT architecture that is shown in Figure 1 is the primary focus of this paper. The proposed methodology consists of designing a structure of an edge gateway and a hybrid router in the edge layer. This specifies that design will be discussed in the slides that follow. In addition, the software that is used in the implementation of gateway is similar to the architecture of IoT, which is displayed in the Figure 2. In the continuation of summary, we know that for a given problem setting, the challenges and the solution provided are given below and is implemented in 3 real-time case studies in our paper that will be covered in the next part of the presentation. In order to develop effective solution for short-range wireless internet protocol application that call for a real-time and low-latency feedback, the IoT heterogeneity may be improved with the use of hybrid routers, and these routers also give a higher quality of service. An integrated environmental sensor known as BME 280 is incorporated in long range, as in LoRa networks. This sensor is used to determine the temperature and relative humidity. In one of the case study is the case in the area immediately surrounding the router. As a result, the router itself can be utilized as an environmental sensor node to detect the surroundings. As you can see here, we have two major problems, that is number of gateways are more and the cloud computing issues. So for gateways, because short range wireless protocols such as BLE have a limited range, you will need to connect to a number of different gateways in order to access the IoT, that is internet over a wider area. To resolve this issue, we are using a hybrid router approach. In this, a hybrid router improves coverage by combining the long-range wireless technologies referred to as a LR-WAN, LoRa in this study, with the short-range wireless technologies referred as a BLE in this paper. In this edition, offers the prompt responses in addition to fundamental edge jobs, taking readings from the ecosystem in the surrounding area. The second issue we had is cloud computing issues. The most significant problem is the increasing number of latency. As the number of devices and the amount of data continue to grow, bandwidth is becoming a constraint. Also, interrupted IP protocol connection. The fact that the cloud server is located at a greater distance from the IoT nodes causes the IP to be unstable. As a result, users may lose data access to the internet. For overcoming this, the solution provided in the paper was to use an edge gateway, which offers a low-cost, locally based edge services for a variety of IoT devices. including device management, cloud storage, and data management. In a contrast to a cloud computing system, edge computing is more reliable since it allows for a provision of mission critical function locally, should that become necessary. The next is the hardware implementation. As you can see from the figure, IoT gateway implementation. Here we are using a Raspberry Pi, long range module, XB modules, and BLE modules. Raspberry Pi is used as the main controller in the IoT gateway prototype. Also, Raspberry Pi comes equipped with Wi-Fi, Ethernet, and BLE modules, which are already installed. The purpose of the PCB, that is printed circuit board, is to integrate LoRa and the XB with the Raspberry Pi controller. Raspberry Pi receives its power supply from an external sources, while other network modules receives either 3.3 volt or 5.0 volt supply from the Raspberry Pi itself. To have a complete command over every network module, a low power switch dedicated to each radio frequency connected to the Raspberry Pi through SPI or UART protocol. Two LoRa modules, that is long range modules, has been attached, each of which has a capacity to support a unique modem configuration. In addition to two LoRa modules, two XBs have been included to facilitate a long range connection. Also, the BLE dongle is linked to the Raspberry Pi using its USB port. The next part is IoT router implementation. In given slide, we can see the block diagram and the router device. The prototype of the router, which has an integrated temperature and humidity sensor, in addition to a power management unit, that is PMU, and a high performance microcontroller, that is MCU, BLE, Bluetooth Low Energy, and the LoRa, which is long range. An energy harvesting unit, whose model number is ADP 5090, a buck boost regulator, model number used is LTC 31301, and an energy storage unit are the three components that makes up the power management unit. Here it is a 2600 milliamp rechargeable lithium battery. The MCU is based on Nordic's NRF 52840 system on chip SoC, which is an innovative and high performance piece of silicon that supports numerous wireless protocol. In other words, the router functions as an on-field sensor node and uses the network protocol BLE5 and LoRa long-range module to transfer the data that is collected from the onboard BME to AT in order to determine the temperature and humidity. So the next part will be covered by my teammates.
And I will explain the strength of this system. The first strength is scalability. As per proposed hardware and software architectures, the system can be scaled according to the requirement of number of sensor nodes, hybrid routers, and gateways. Right now, the case studies were performed on limited number of nodes, but in a real-time system, hundreds of nodes will be connected to the multiple routers and gateways. If the router or gateway are not in a range with sensor nodes, then we can use more number of routers and gateways as per requirement of the application. To verify the system's capability, our experiment is performed on YORHA-SIM, which is simulator for YORHA systems, which will calculate data extraction rate and spreading factor of the systems. Here is the graph of the analysis. We can see for fixed SF is equal to 9, the data extraction rate is greater for the 15 intervals, and for 10 and 5 interval it is reduced to 0.98 and 0.97. Another field testing is done on this, in which SF is kept constant at equal to 9 and bandwidth of the system is 125 with 5 number of intervals, and the packets were successfully received with data extraction rate of 0.991, which proves that system can be scalable. The second strength is flexibility. flexibility in transmitting sensor information via Bluetooth or LoRa. So this variable sensor node consists of LoRa and Bluetooth with low energy. So for short range protocols, Bluetooth can be used, and for long range, LoRa can be used. This is very advantageous because sensor node is directly in range of Bluetooth and the gateway. The sensor node will transmit only through Bluetooth, else it will transmit through LoRa. Increasing the range of transmission of short range protocol, which will save the energy. Even if gateway is out of range, the LoRa range of sensor node, it will transmit the information to gateway via hybrid router. This variable sensor also consists of hardware energy harvesting. In this, it can save the energy from the solar, which will use in the usage of the this microcontroller, and it also consists of low power boost regulator, which will consume very less power consumption. So this sensor node has the BME 680, which has temperature, humidity, and pressure and gas sensor, along with feature of energy harvesting and transmission protocols like Bluetooth and LoRa. This can be used in other applications in standalone settings in the different sectors of the IoT like agriculture and motor vehicles like that. Third strength of the system is increased lifetime of hybrid router through energy harvesting. So as we can see here the router device and block diagram of this hybrid router. So this hybrid router consists of three main power management unit, which includes energy harvesting unit, buck boost regulator, and energy storage unit, which is 2600 milliampere lithium ion battery. So as we know, the lithium ion battery can be easily discharged within 2 or 3 days of normal operations. So to increase the battery life of the hybrid router, the energy harvesting circuit with buck boost converter for continuous power supply is included. So this ADP 5090 is very high efficiency and ultra low power energy harvesting chip with maximum power point tracking and charge management function. It can convert DC power with more than 80% conversion efficiency from this solar panel into the rechargeable lithium-ion battery. So this solar panel is commercial 55 to 67.5 millimeter with 310 megawatts of power is chosen for this application. So according to this paper, this energy harvesting setup could make hybrid router work continuously for 9 days in indoor setting with 12 milliampere of continuous power of operations, which is very great strength of this system.